So, good evening. Tonight I'm going to explain exactly on how the fuel divider or the fuel distributor, what we call it, actually works in terms of how it distributes that equally and what internally happens to this. And then we're going to look at the relationship between the plate displacement and how far this thing actually comes up. Just a little peek here. You can see it. I will explain that in a second. So here we got now the fuel metering or the air metering unit. And the way this works is the vacuum is applied from underneath from the intake system, and as more vacuum you got, as more this plate is displaced downward. That in turn pushes this little plunger here, that roller up, and that little roller will then push this rod or the piston actually of the fuel distributor in. Now, as you can see, we have a fairly large movement here. We can do here all the way down, and you can see on how limited actually the movement is here. So I have this now flat laying on the table, and the displacement is not the full motion than if the thing is slightly higher, and I will show this here in a second too. What I want to show you is actually the measurement in this position, and then I have written down the numbers. I'm going to put the meter on here, and now we go up and we should see this. I have calibrated this thing as good as I can. It's a little bit of a crude setup, but it is more to demonstrate the actual translation of this. Let me see if I can zoom in, and if we can get this here. Yeah. Actually, let me move this whole thing a little bit over. So now I'm going to do the most displacement I can do. Actually, I have to, oops, let me see, there it goes. We're going because it is coming up. So now we have 100 mil, 113, that's about as much as I can do. I measured it earlier, it was about 110 mil. As this is 110 mil, is this scale here is 1/1000th of an inch, so 1 mil basically. And the displacement we have measured on the other side is this here. Whoops, I didn't want to show you all of this stuff here on the kitchen counter. Of course, now I got grease on my fingers, and now I can show you this. The plate here, actually, this displacement here is 0.714 inches, or 714 mil, and we moved about 113 now. I moved 110 earlier. That is this number here. This here. That gives us a relationship of 6.5 to 1. So this is basically a correlation. When this plate here moves further, then the plunger is going to be moved up, and it is not a linear function. The displacement will actually increase as further this plate here moves down. And as we can see it, I can move this even further down when I angle it, because I need a bottom clearance. It basically comes out until this arm here goes past the edge. You can see this. This is the full motion. The full motion on this here is from the top position where it is set up right now. It's 2.419 inches. That's the complete travel, or 6.144 centimeter. Then the displacement back here goes for the full range 235 mil, or 0.235 inches, which is 0.6 centimeters about there. And that gives us a divider of 10 to 1. You can see how dirty the thing actually is on my fingers here. I got the print now. You got my fingerprint on here. And so this is not a linear function, but a logarithmic function. So we're starting out with a very narrow or very small relationship where this is almost 1 to 1. And as further the plate here is depressed, as more vacuum we apply, is larger, the ratio actually becomes between actual travel of the plate versus displacement of the plunger or piston of the fuel distributor. So that is the basic thing to know. The curve basically looks like this here. If we were to draw this, it goes up like this, where the starting point here, basically, if we make a line here, it's not very straight, where this line here is actually the ratio over the plate travel. And what I mean by plate travel, which is this here. So this is the ratio increases as further this plate goes down, as higher this number becomes. That's basically it. So we have basically what we're starting out here with a 1-to-1. And then somewhere back here, we're at a 10-to-1. And this is the logarithmic function. And most of the action happens between here and here. This is fuel starts. And this is basically throttle full open. Right here, full open. Throttle full open. So this is our working range of our fuel distributor. And this here, when it starts here, this is what we're calling that play on this plate. And there is a question which has arisen: do you have to have a play or not? That depends on the overall condition of this assembly here, on how well these parts in here work, on how dirty this is, whether that is freely moving or it is stuck, and the overall condition. And this play can be adjusted with this Allen key here, and that also offsets the knee, basically, and that is your duty cycle when the unit is fully warm. So this is adjusted with moving this knee up or down with the Allen key. You can move that set point further down here, then you're gonna have a leaner mixture, and if you move it further here, you're gonna have a richer mixture. And that is basically the function of this. And the vacuum applied on the bottom side equates an X amount of air flowing from the top into the engine intake, and that has to be mixed with a amount of fuel which is measured in liters per minute. And when we take a closer look at this on the fuel distributor, and actually it is not a distributor but a divider. In this case we have 8 outputs, which are from here 1, 2, 3, 4, 5, 6, 7, and 8. This here is the output to the cold start valve. This is where the EHA valve sets up. I'm going to talk about this here in a minute. And this here is the fuel inlet, and this is the 2 return lines and the internal pressure where it comes back from the pressure regulator. This is the unit I bought of eBay. Now let's start with the EHA valve, which is the simplest part in this. This one, the EHA valve, as you may know, has a internal set screw, which has a cover screw on it. And when you take the cover screw off, you can set this. So when you measure the pressure on the lower chamber, which is this port here, you open it up and you put your fuel gauge on there. And for the system pressure, you basically disconnect your cold start valve and you put either another meter on there or a switchable fuel tester kit. You can use 2. Then this here should show you 6.4 bar, and this here you should be showing you 6 bar at idle speed, basically. And when the EHA valve is electrically connected, that set point of 0.4 bar difference between top chamber and lower, or upper chamber and lower chamber, is set via the set screw. By going counterclockwise, you can decrease the differential between the two, or you can increase this by going clockwise. So And when the fuel distributor or fuel divider is calibrated to have an equal amount of fuel coming in proportionally to the fuel going into the main outlet, and then with the pressure regulator actually attached to this, the way the pressure regulator is also a divider, it will maintain a certain amount of fuel in here depending on the setting of your plunger. When the plunger is in the out position, there should be zero fuel flow out of any of those 8 ports to any one of the cylinders. And as you can see, each cylinder right underneath has a screw here. And of course, if I'm not going to say it, these screws actually control the flow, the volume of each individual cylinder. So when the unit is calibrated after a repair, for instance, or when you overhaul that, then you have to connect 8 fuel gauges or fuel flow measuring devices on here, and you screw in your fuel pressure regulator, 2 fuel pumps, and a fuel filter. And you can use the Bosch used to have a blank unit for this, or you can use a new EHA valve for it where you know it has been calibrated to 0.4 bar differential between the two. Then you adjust this here where you start on cylinder number 1, and you have to have a little displacement. And usually what they do is they measure this from all the way out to all the way in. This here, before it starts, is the 0% position, and fully in is 100% position. The fuel flow is adjusted first at 5%, which will get us into this lower part of the knee, right about here, where the fuel flow basically starts. That's about your idle position, is somewhere between 3 to 5% of displacement. This is not measured in actual physical, but only between where it starts until it ends. This is 100%. This gives you your scale. And they have on the setup, the fuel distributor or fuel divider is set up, is connected with 8 hoses here. They connect a pressure meter here, and they hook up a pressure meter here to monitor the 0.4 bar differential plus the 6.4 supply on the supply line, which is this here. And then the return line just goes back into a tank. And then they have a micro adjuster that is basically a rod which is coming in because this is held in a fixture. And you come down with this here, and then you go and you set this, you measure this. This is 0, 100, and then they have a dial gauge on there where they can set this to 5%. And then they have, you look at all 8 gauges for your flow, and you start to adjust 1 to whatever value you need in terms of liters per minute. I can't remember what that was. And then you adjust the first one, and then you bring all the other ones into synchronization. And they should be, if this is completely rebuilt, properly rebuilt, and the entire system was cleaned in citric acid in about at 85 to 90 degrees Celsius for half an hour, then the fuel flow achieved should be within 0.01% of each one of these adjustments here. That means that's the fuel coming out on the backsides. And that's how this is adjusted. They do this with electronic flow meters. These are basically, they have a little turbine in it. They're highly precise, very expensive. And they go to a digital display, which can display that in 347 microliters. 1 microliter is 1 millionth of a liter. So this would be in 347 millionths of 1 liter accuracy. That's how this is set up. The lowest cost sensor I could find to actually build something like this would be about $130 for one sensor, and you need 8. If you go with the name brand stuff, all stainless steel sensor and this, that, and the other thing, the highest quality, they're gonna cost you about $1,000 to $1,500 per sensor to actually build the test fixture for that. They have a pulsed output. They operate of plus minus for plus 5 volt and 0 volt, and they have a pulsed output. And you go into a precision counter with this, and that precision counter in the software converts this to the actual flow rate in liter per minute, set to 0.001 digit in liters. So this would be, oh, what would that be? 1/10,000th of a liter increments. That's how they're actually set up. And I built 10 of these test devices for Bosch back in 1987. This was one of the first projects we actually did. And Bosch winded up buying the flow meters, the flow sensors itself, and they spent $28,000 for one of these flow sensors. And you have 8 of them, and we built 10 stations. Bosch had invested millions of dollars into this system for the CIS, especially the second generation. This is the same fuel distributor or fuel divider you're gonna have in the Rolls-Royce and the Bentleys beginning from 1991. Until 1991, Bentley and Rolls-Royce used the earlier version with the warm-up regulator, what you find in the first generation W126. And when Mercedes discontinued the 126 second generation in 1991, that's when Rolls-Royce adopted this very particular system, exactly as it is here, with the same base unit here, into the Bentleys and into the Rolls-Royces, all of them. They were all, this was the state-of-the-art mechanical fuel injection system in the 1980s, and basically in the 1980s. And it was a direct consequence of the United States emission standards which were introduced. So this gives you an idea. Again, so you get an equal amount out. Now, if you're trying to do this with beakers and you're trying to use the stopwatch for it, you're probably gonna lose your hair. If you have watched repair videos of this here or rebuild videos, you will see the people putting the associated parts with each cylinder or port into a particular bin when they're taking that apart to make sure it gets back in the same. And the reason why is because they don't have the ability to accurately adjust the actual flow. But basically after every rebuild, you have to adjust the flow to be in the most precise equality between all 8 cylinders. And the reason why they had such a high standard in this was this is really the pinnacle of German mechanical engineering. This thing is all math and mechanical engineering, and the precision in this is phenomenal. And what they did here was they set this to very, very high tolerances in order for this unit to last 15 years or 150,000 miles. That was the life expectancy Bosch had designed this part for. If the car has been very well maintained and garaged in a dark environment and no ethanol fuel, you probably can get these here to work for 20 to 25 years. But they will deteriorate over time. And the first issue you're gonna have with these here when they're getting imbalanced, what that means is you don't have an equal amount of flow coming out of fuel in volume going into each injector, is that the engine is gonna have a rough idle. And as worse this gets, as more this is off between the different cylinders, as worse the whole thing gets. The whole matter is complicated by the aging of the and worn out injectors when they don't open in the correct pressure anymore when they're too far apart. That will increase the whole issue. I have a fellow down in Texas I'm working with. He has a 300E, and he bought a used fuel distributor like I did for his car, and we're going to get the rebuild kits from Germany for those, and I will see that I'm going to build actually a flow station where we can test this and adjust this to 0.01% accuracy, except that I'm not going to be spending thousands of dollars on each sensor. If I'm going to go, I'm going to go with the $125 sensor, which is probably going to yield a 0.01 accuracy in adjustment, which is 10 times less accuracy than what Bosch had in the first place when they built it. What complicates the problem in adjusting these sensors or doing these tests is that they have to be actually performed with regular gasoline, with premium or super, at the correct octane rating. In the United States it would be 91, in Europe it would be 95 or 96. And of course that, the issues here are absolute cleanliness and then fire safety. You can't imagine when you set this up, this is difficult to do indoors if you don't have a correct fire and ventilation system, fire suppression and ventilation system available, and it has to be done at a steady temperature, at room temperature. The ideal temperature for calibration is 72 degrees Fahrenheit. Just to give you an idea, in clean room conditions are ideal because you don't want to introduce any type of dust into a rebuild or brand new unit. And the same thing applies through the cleaning process and the reassembly with the new gaskets and new parts and O-rings and everything, is you want minimal, if no dust, if possible. So clean room environment with hairnet and mask and protective clothing is advisable. This is how sensitive they are. Is more cleanliness and more precision is applied to this, as longer they will last and as better your car will perform and run and with the idle speed. So even if you have a slightly worn valves and that sort of stuff in your head, this will eliminate most of the rough idle. The valves, that depends on what they are and what condition they are and that sort of stuff. But it will eliminate quite an issue, because this is where most rough idle issues are coming from, is from the fuel distributor. So if you have any more questions, and this is one of the videos I hope I'm going to be able to make you in the next 3 to 6 months, is to do the test station for this, the high precision test station, which should cost hopefully under $5,000 by the time it is done. But I'm going to build it anyway so we can properly document this here on YouTube, so you can actually see this on how this whole system is actually fine-tuned down to the dot, basically like almost what race car drivers would do. So this is the precision which comes in it. And with that, if you have any questions, please feel free and leave them in the comments, and then please subscribe or like the video if you do. Otherwise, we will be seeing you soon, and happy Mercedesing.